Okay, so we've spent most of the semester talking about Rn. We're going to move into some more general metric spaces now. What we're really going to care about in a lot of the examples that we're going to do involve spaces of functions, for example. So for trying to do applied math, usually there's some functions that we're looking for or some differential equation that we're trying to solve. So these are the natural spaces we want to work with, but metric spaces can be almost anything. So we'll give some general definitions and results, but with the goal of heading towards solving some concrete applied math problems, and we'll have some examples to that effect over the next couple weeks. So this is 8.1. Okay, so what is a metric space? A metric space is a collection of objects together with this thing called a metric, which gives you some concept of a distance between objects. And there's basically three properties this metric has to satisfy. So a metric space, all right, is some collection of objects, at least one object, okay, together with a metric. Okay, a metric is just a function of two variables. So rho is going to take two variables, both from our set A, and it's going to return a real number. Okay, and what does this have to satisfy for us to reasonably consider this a useful distance function? Well, for all, say, u, v, and w in our set, we want these things to be true. The distance between two objects is non-negative. Okay. So we want this to always be true, and it shouldn't just be a flat zero. It should only give us zero if I happen to put in the same object twice. So a distance from something to itself is zero. Distance from something to any other object is positive. Okay, so with equality, if and only if u equals v. That's, I think, reasonable to stick it as a requirement for a distance function. Another fairly reasonable requirement is a symmetry condition, that the distance between u and v is the same as the distance between v and u. And then finally, we want some kind of triangle inequality. Okay, that the distance from u to v, somehow rho gives us the shortest distance between u and v. So if we decide to stop at somewhere intermediary along the way, that's taking us off the shortest path potentially. So going from u to w, and then from w to v is somehow more expensive. Okay, and we call rho a metric. So we're completely used to working with metric spaces. So we've been working with metric spaces all semester long. We just haven't used this language. But I mean, an easy one would be to say A is the collection of all real numbers, and my metric is I just take the difference between these two things and look at the absolute value. So that's a usual metric that we're accustomed to working with. And since our intuition was formed in R or Rn, our intuition about metrics was formed here too. So we kind of, the things that happen here don't surprise us too much. Other metric spaces you find may surprise you a little bit more. So another possibility is, my collection of objects is it's really just a collection of objects. It could be anything. It doesn't have to be numbers. So I could form a metric space out of you guys. I could take each one of you and stick you in my collection of objects. Okay, so A is just the collection of all students in this class. That forms a set, no problem. And now I have to come up with some kind of distance between you, some kind of metric. There's plenty of ways I could do it. I could just, look at where you're sitting and do a Euclidean distance between everybody. I could do other things. I could just have a metric that says, tell me if these two people are the same person or different people. And that would also be a metric. This is called the discrete metric. So I could have a metric like this that says, well, if I compare a person to themselves, the distance is 0. And otherwise, the distance is 1. Okay, and this is still a metric, right? It satisfies the positivity that we need, right? The only way it's 0 is if I put the same person in twice. It's perfectly symmetric. And it does satisfy a triangle inequality, because the left-hand side is going to be either 0 or 1. The right-hand side, well, if this is 0, it's automatically, we're done. If these two guys are different, then the left-hand side is 1. And that means U and V are different. That means either U and W are different, or W and V are different, or they're all 3 different. At least one of these terms is 1. So left-hand side is either 0 or 1. Right-hand side is going to be either 1 or 2. So we do have a triangle inequality. So this is still a metric. This satisfies our usual expectations about a distance function. I'll come back to this example a little bit later. We'll see that your intuition was formed in Rn, and this metric is not going to do all of the things that you necessarily expect it to do as we move along. Now, often we want metric spaces that come from a collection of objects that have a little bit more structure. So a lot of times we're interested in a metric space that's somehow derived from an underlying vector space. All right, so a vector space has a little bit more structure. We again have a collection of objects, but now we can do things with these objects. We have an operation called addition, and we have an operation called scalar multiplication, and they satisfy some simple rules. And then we can imagine trying to put a metric on this kind of collection. So vector space is a non-empty collection again. Set of elements or vectors. Okay, together with 2 operations. Which we'll name addition and scalar multiplication. And these also have some properties we require them to satisfy. Okay, so for all objects in our set, and for all real numbers, R and S. All right, I'm going to write these out quickly and not spend a lot of time on this. You've seen vector spaces before, but I just want to quickly remember what this is. Okay, one of the biggies is that it's closed under addition. So if I add 2 objects from my vector space, I get another object still in my vector space. Okay, the operation of addition commutes, so I can do things in any order. another way I can change the order of operations in addition is to move parentheses around. What else? There's a 0 element. Okay, so there's an object that we call 0. Okay, and if I add it to any other object, nothing changes. We have an additive inverse. Okay, so every object has an anti-object. So for all u, there exists some object called minus u in my vector space, such that u plus minus u gives me this identity. It's closed under scalar multiplication, so a scalar times my vector is also in my set. What else? We can multiply through scalars. Okay, we can multiply them through this way. We can also multiply them through when we're adding the scalars. What else? We can move brackets around when we're multiplying things. So we have a lot of flexibility in order of operations. And it's true that the number 1, a real number, not thinking of 1 as an element in my vector space, 1 is just a real number, one of these scalars, acts as a kind of identity element. Multiply 1 times any vector and I get that vector back. So, you don't have to be able to spit this list out from memory. We're going to be playing with these objects, and then sometimes what we'll care about is we have a vector space, and now we're interested in a vector subspace. So taking a subset of that object is still somehow a vector space. So the big things to worry about when you're doing that, most of these properties will still hold. If you start with a vector space, you take a subset of those elements. Most of these properties are still going to hold. What do you have to worry about? Big things that you have to worry about is that you still have closure. Okay, so that if you've decided to include u and v in your subspace, you have to include u plus v. If you decide to include u in your subspace, you have to include any constant times u. Now, a possible constant is 0. So you kind of get your identity elements for free here. So these are the two maybe that I want you to remember, is that if we start playing with subspaces, you need to make sure your subspace is closed, that you're not going to suddenly do an operation that lands you outside of your collection of objects. Aside from that, if you have some intuition about this, don't memorize this by rote, because that's not how you're supposed to spend your time doing. Now, we can push a little farther. We can add more structure and say, let's add a norm to this, some kind of function that acts on our vectors and somehow tells us something about the size, I guess, of our vectors. So our normed vector space we have a vector space, of course. And now we have some kind of real valued function on it. Okay, so together with a function that I'll call n, that takes objects in A and spits out a real number. And again, there's a couple properties that we want. Okay, satisfying that for all elements in our in our vector space and scalars. Okay, so again, the norm is supposed to tell us something about somehow the size of an object. And so we add on here some conditions that we would like. Again, we're going to have a positivity condition that when we start talking about the size of an object, we want it to be non-negative. So the norm of u should always be non-negative. And we should get equality only if we're talking about this zero element. If I take an object in my vector space and multiply it by some constant, I want to think of the size, the length of this object as being just rescaled by that constant factor. So that's the next condition I have for my norm, that if I take u and multiply it by a constant, this should just be c times the norm of my original absolute value of c, because we know we get positive or negative constants here. Okay, and then again we have something that looks like a triangle inequality. That if we take the object u plus v and look at its size, well, we know that u plus v, I mean, things might kind of combine to make it bigger, or there might somehow be some cancellation that makes things smaller. This is going to be less than or equal to norm of u plus norm of v. Okay, and we write that n is a norm. So how do I go from a norm? We're trying to talk about metric spaces. Now I've said, let's pretend we're working with metric spaces that have a ton of extra structure. So now I'm working on a normed vector space, and from this, now I want to put a metric on this. So what's the easiest way to put a metric on this? Yeah.
You do like the norm of the difference?
I could do the norm of the difference. That would be an obvious way to, I hate to use the word obvious, that would be our way, a simple way to do this. You can always do this. But that maybe doesn't see any of the structure that we have here. Yeah, we could look at the difference between two objects and use that as our distance between them. Take the norm of the distance. So that is a very natural thing to do. And we can call that the metric induced by the norm. So this is a little theorem that is not hard to prove. So if A and N form a normed vector space, then we can define this metric by the norm of x minus y, and this is indeed a metric. It does satisfy the properties that we need. So the proof is not long, but it's worth just being aware of what we have to prove when we're trying to show something as a metric. There's three things. So we have this positivity. Well, norm satisfies positivity, so that's kind of automatic. And when do we get equality? We get equality if and only if x minus y equals 0. That's a property of the norm. And that, all right, if you really want to, you can try to take that and prove from here that that implies x equals y. I'm just going to state it. Okay, so that's a check. We need symmetry. So I want to take this and somehow write this in terms of rho yx. So what I really need is norm of y minus x. Now, y minus x is not the same as x minus y. It's a different vector, of course. But they're not totally unrelated to each other. They're related to each other like this. In fact, I'll write it explicitly as minus 1 times y minus x. And, well, the property of a norm is I can pull this constant out in absolute value. So this is the absolute value of minus 1 times the norm of y minus x. Which indeed lets me swap the order of these inputs. Okay, and finally, triangle inequality. That comes out, I mean, pretty automatically because we already have something that looks like a triangle inequality. So rho of xy is the norm of x minus y. I need to bring in an intermediary somewhere. So I just bring it in. And now this has the form I need to use this inequality. This is x minus y. This is, this is x minus z, and this is z minus y. And this indeed gives me the metric at two different places. So the metric x to z plus the metric from z to y. Okay, so this works. Anytime you have a normed vector space, you can always build a metric space. Not only that, I mean, anytime you have a collection of objects, you can build a metric space on them. But anytime you have a normed vector space, you could build a metric that hopefully inherits a lot of the structure of your underlying normed vector space. And that, of course, is appealing when you're starting to think about problems with a lot of structure where there are functions and maybe there's properties of continuity or derivatives. And you want to carry information about those things in your metric somehow. Okay, our default metric so far, so again, we've been using metric spaces all semester long. We just haven't used the language metric spaces. But all semester long, so far in RN, we've been using this Euclidean metric. We just haven't said so. So our default has been to use the Euclidean norm. So we start with a vector space. Rn is a vector space. It's a normed vector space. We put this Euclidean norm on it. And then when we need a metric, we use the metric induced by this Euclidean norm. So we've been using this norm here. Right? We sum the squares of the components and take the square root. Or if we want to look at the distance between two objects in Rn, which we've certainly done, then we say, well, this induces the metric. Same kind of structure, and now in place of xi, we have xi minus yi. This is certainly not the only norm that we could put on Rn. And sometimes there are other norms that are preferable. It really depends on the problem you're trying to solve, what norm is going to be most natural or give you the most useful information. So another whole class of very common norms are the p-norms. Okay, so we're going to say that for p greater than 1, the p-norm of some vector in Rn is so it looks almost the same as what we had, but now we're going to take pth powers instead of second powers, and then we have to raise it all to the 1 over p power.
P in Rn, or is it natural?
P could be in Rn. It can be it doesn't have to be a whole number. You can see that I think that you need to raise to the 1 over p power because we want to be able to pull constants out. So if each one of these xi's is multiplied by a constant get raised to the p power all the way through, then we need to take the pth root of out to be able to have the constant come out. And with p equals 2, of course, we get our favorite Euclidean norm, which is wonderful for many applications, but not all of them. And this is a norm. You can check that this is a norm. Two of the properties, okay, I just waved my hands a bit and argued that this property holds because we're taking the pth root. The positivity property clearly holds. There's nothing to do here. The hardest one, almost every problem, the hardest one is part C. There's this triangle inequality. So the first two properties of our norm are kind of fairly straightforward. Then the triangle inequality is where all the work usually goes. Well, if p equals 1, I'm going to do the case p equals 1, and then I'm going to cite another result for p greater than 1, because there's just more technical details that are not super exciting. If p equals 1, this is not hard to see, I think. So x plus y to the 1 norm. This should be absolute value, actually. Sorry. All of this, an absolute value to the pth power. If that matters to get positivity, certainly. So this is, now we're just raising things to the 1th power. So this is just the absolute value of these things. So things to the 1th power, and then we take the first root, so nothing to do there. And okay, these are just real numbers. They're not vectors in Rn. These components are real numbers, and we can do our usual triangle inequality to say, well, that's less than or equal to the length of xi plus the absolute value of yi. And then you look at this and you say, well, this first part really is just the 1 norm of x, and the second part really is just the 1 norm of y. Okay, p greater than 1, you need some technical inequalities to get there. I'm going to basically state it. The proof is in your book, so you can check it out. You don't have to just believe me. But I'm not sure it's worth our time to argue this technical inequality. This is Minkowski's inequality. So for p greater than 1, okay, and it says, it basically just says what we want it to say right now. If p is greater than 1, and we have all of these components U1 to UN, V1 to Vn. And these are all non-negative. Okay, then if we write down the thing that looks like this, but now we do the p-norm version of it. We don't worry about absolute values because right now I'm just assuming that's positive. Then, okay, ui plus vi to the pth power all to the pth root is indeed less than or equal to what happens if I split these up. And this immediately yields the triangle inequality for the p-norm. So this is one collection of norms that one might want to use. L1 is common in some applications. It does useful things. L2, of course, is very common. Other weird norms come up in some technical PDE theory, for example. Another thing that you can ask is, well, how big can we go here with p? What happens if I take a limit as p goes to infinity? Any guesses or educated guesses, or non-guesses, just answers that you can see are true. What happens to this as p goes to infinity? Yeah? It approaches the largest component, exactly. The absolute value of the largest component. Okay, so we can check that. I mean, I think many or most of you have seen that stated before and may or may not seen it proved. So we can define the infinity norm. And then, of course, we can check is it actually a norm. Things that are true everywhere in a sequence don't always hold in the limit. We've seen that happen before. Just a sequence of functions that are continuous, and all of a sudden the limiting function is not continuous. Properties don't always push through the limits. But this property of being a norm does. So the infinity norm of x is defined as the limit as p goes to infinity of the p norm. Let's put the p where it belongs. Okay, and indeed, as Jack suggested, this just gives us the largest component. And this is also a popular norm for some applications. I'm an infinity norm person myself, but depending on which faculty you talk to, some of them love the two norms, some of them love the one norm. It depends on your problem. So x infinity is the largest of all of these components. Maximum is not a problem here because there's just a finite number of things that I'm taking a maximum of. Okay, so let's try to prove it. So I'm going to give this a name so that I don't have to keep writing all of this out. I'm going to call this M. So M is this maximum. Okay, so what do I need to do? I need to prove that M is equal to this infinity norm, which we define through a limit. So one way to prove things are equalities is to prove that the infinity norm is less than or equal to m, and also that it's greater than or equal to m. So you're not trying to do all the work at once. This infinity norm comes from doing a limit, so we really should be looking at what happens for finite p, and then see what happens as p goes to infinity. So all I'm going to do, I'm going to write this, and then I'm going to do two things. I'm going to write greater than or equal to, and I'll define what it is, and then I'll write greater than or equal to, and try to get some inequalities that involve this quantity m, and see what happens in the limit, and then I'll do it for inequalities facing the other direction. So let's first write what this actually is. All right, so I'll come to you. What's a way I could write down an inequality that brings m into the picture, this maximum component? It's less than or equal to the sum of the maximum. Sure. So each of these is less than or equal to m. So that's the obvious place to start. So for any p, this is true, that this is less than or equal to the sum of these m's to the p's. Well, now I'm just adding up a constant. I'm adding it up n times though. So I'm going to have n m to the p to the 1 over p. So n to the 1 over p times capital M. This is kind of almost what I want, right? At the end of the day, I'd like to say that the infinity norm is less than or equal to m. I have this prefactor here, which I don't want. Now, this prefactor holds for finite p, but there's one more step, of course. We need to take a limit. We need to do this. So this is going to tell us that the infinity norm is less than or equal to, well, m is just a constant, the limit as p goes to infinity of n to the 1 over p. And what does n to the 1 over p approach?
0. Or sorry, 1.
1, okay, you caught it, yes. So 1 over p approaches 0, so n is just a fixed finite number, it's not changing. So indeed, this approaches 1, so this is exactly equal to m. So that gives us the bound we want in one direction. And now we've got to turn it around and go the other direction. Okay, so once again, I'll start with my p norm that we're going to take limits of. I'll write out what it is. And now I know I need an inequality that faces this direction. How do I feed m into this? The summation of this over the maximum? How do you mean? What do you mean by the summation over the maximum?
The summation of the alpha value of xi over the maximum value of xi.
Over the maximum value of xi. So we did the summation over the maximum here. I think you're kind of almost on the right track. We need to make sure that whatever's here is bigger than or equal to whatever I put here. The minimum isn't going to help because what if the minimum is 0? That does not give me m. All right, so let's put in one little extra bit of information here. M we've defined to be the maximum component, and it's equal to one of these components. So let's let m equal xj for some j. Some j between 1 and n. This is true. Now if I come back to my sum here, I'm summing up a bunch of things that are all positive. So that's certainly bigger than or equal to, because this is the direction I need my inequality to go. This is bigger than or equal to what happens if I exclude most of these. Right? The sum includes this term and then includes a bunch of other terms which I've just thrown out. I mean, it looks like I've just thrown out most of the sum. It looks like I've done something quite dangerous. And this is equal to m, so this simplifies right down to m actually. So actually for finite p, the p norm itself is always going to be bigger than or equal to this maximum component. And it's always going to be less than or equal to this multiple of the maximum component. And in the limit, as p goes to infinity, well, this prefactor goes to 1, and all of a sudden these bounds close in on each other. So this indeed means that if it's true for all p, it's also true in the limit. The infinity norm is a norm. You know, I've said properties don't always go through the limit. In this case, we're working with fairly simple properties. Essentially all the properties we have are just simple inequalities, and these inequalities are preserved in the limit. So this is always important not to assume. You write down something that you think looks like a great way to define a size of things that would be useful to you. You can't assume it's a norm. You have to prove it's a norm. But this guy indeed is. Okay, I'll leave it to you to check this or check your textbook. It just consists of writing down that these properties all hold for the p norm, and then in the limit, the inequalities all still hold. So that's as p goes to infinity. Now, we could also consider the vector space Rn and let n go to infinity. So what are the elements of my vector space if I do this? There's this infinite list of things. There's a name for that.
Sequence.
A sequence, yeah. So this just gives me sequences. Okay, so R infinity is just sequences of real numbers. So sequences of real numbers. Okay, so these consist of vectors of the form things that have infinitely many components. And we can define addition. We can define scalar multiplication in the obvious way of just add the components together. So x plus y is just adding the respective components. Constant times xi is just, constant times x is just the constant times the respective components. And this indeed will give us a vector space. And then we can start taking, this is where you may want to start taking subsets of things and looking at vector subspaces. Collection of all sequences is large and maybe too large for what you're trying to do. So we may be interested in subspaces, vector subspaces of R infinity. And a typical way to do this would be to start by defining a norm on R infinity, some norm, and then say my subspace is going to consist of all objects that have a finite norm. And being finite is not going to be at all necessary or obvious for things in R infinity because there's infinitely many things to look at. Even if each element is finite, and we know that things can grow, or if we're trying to sum up things, even if they're small, we could get something that blows up. So the approach would be to define a norm. Now, to have a normed vector space, the norm has to spit out a finite value. It has to spit out a real number, right? So just defining something that looks good as a norm isn't going to make R infinity a normed vector space unless the norm spits out a real number always. Okay? So then we define the subspace to be everything in our space such that the norm of X is finite. All right, so we could define the same kind of p-norms that we had before. Right, this involved a sum from 1 to n, but now all of a sudden we've taken n to infinity. We're working with infinite series, and it's of course not at all obvious that these series converge. They could converge or they could diverge depending on what kind of sequences we put in. So, as an example, let's take p between 1 and infinity. And let's let xp equal now the infinite series okay, and then we say, well, let's use this to create a vector subspace. So a vector subspace is, for example, we might call this LP, little LP. And now this would just be the collection of objects with finite norm. All right, so we come up with this subset of objects. Great, good for us. I can't just, I was very bold here. I called this a vector subspace, but I can't just take any old subset of objects and declare it to be a vector subspace. So one thing we should ask is this, that is LP, a normed vector space? What things do we have to check? I have to check that it's closed under addition. Yeah. and scalar multiplication. And I should probably also check that this is actually a norm, because now we're taking a limit. So those are the things that you want to check. You've got a collection of objects, you've proposed something as a norm, you've taken a subset of them, you need to check these things. Is this a norm? Is this actually still a vector space? And again, we don't need this whole long list of requirements. We started with a vector space. It's just the closure that we need to worry about. Okay, so let me start with, is this a norm? Because answering this question will kind of give us the answer to the question of, is it a vector space? Most of the properties, positivity, no big deal. That's going to be preserved in the limit. Being able to pull out constant factors is also going to be preserved in the limit. Okay, so positivity, I'm just going to say is a check. Constant scaling is a check. Let's do the third property, this triangle inequality. And here we have that, and I want to write this out explicitly because this will be useful in a second when we check the other part of the question, is it actually a vector space? So this was our Minkowski's inequality that I wrote down, and for now you're believing me that it's true, or else you're doubting me and don't believe any of this. Either way is fine, you can check it later. So Minkowski's inequality tells us for finite n, okay, and obviously for finite n, there's no problems doing this. Now, let's suppose that x and y belong to this space. So we know x and y have finite norm. All right, so if x and y belong to this space, they have finite norm, then we take the limit as p goes to infinity, and this, on the left-hand side, as we take this limit, right, this inequality just says that, well, x plus y to the p norm, and the limit as n goes to infinity, we get the p norm. On the right-hand side, we get the p norm of x plus the p norm of y. Sorry, I put this one over p in the wrong place. Okay, so all of these inequalities hold in the limit. Right? This is like a typical comparison type test that we would have done for series. Let's say, partial sums work here, take partial sums here, then in the limit, the same thing is going to happen. We know a priori that these series converge as we take n to infinity because we're told that we did. Yeah.
We also require that x plus y be in the subspace.
Yes, we're going to require that. So assuming we have a normed vector space, we've definitely got a norm. Okay, so, and that's an excellent follow-up question. It's important to check. If LP is a vector space, then this object is a norm. The infinity norm is a norm. But that's our second question. Is it actually a vector space? And again, there's these two questions we have to ask. Is it closed under addition and scalar multiplication? So is LP a vector space? And again, we just want to check these closure properties. Okay, so let's let x and y be elements of this space of LP. I want to check if x plus y is in the space. So how do I check? I have to check that x plus y has finite norm. So we want to know if this has finite norm. This is a p norm. Well, conveniently, I've already written an inequality down here that says, well, the limit of this as n goes to infinity is bounded by the limit of this as n goes to infinity. And this we know to be finite. Okay, so we're closed under addition. Now I also need to check scalar multiplication. So if we also let this be a real number, okay, what do we need to check? We need to check if this object has a finite norm. It's a property of the norm, so that I can just pull the constant out. And now I'm just multiplying a constant by something that we know to be finite. So, indeed, c times x is also in LP. Questions there? Are we happy with these subspaces? Okay, now what do we want to do? We want to basically do calculus on metric spaces. So this was just introducing what is a metric spaces, giving some simple examples of metric spaces, but let's try to build up what we need to do calculus. So let's think back to what were the first concepts that we needed to start doing calculus on R or on Rn. What's that? Integral? Continuity. All right, let's back up even farther than that. Yeah.
Limits.
Limits are pretty important. In order to define a limit, we needed to go back even a little farther than that. We need something about sets. We need a concept of sets, open sets and open neighborhoods in particular. So basically, all the definitions, most of our definitions are not going to change here from what we've done before, but we need to know what a neighborhood is. And as we went from R to Rn, this was the one thing that we kept changing. What do I mean by being close to something? Now, there's a sort of probably a natural way to define a neighborhood on a metric space. Yeah.
Norm is less than, epsilon.
No, the metric, yeah, between two things is less than epsilon, then, okay, this is our neighborhood. Okay, so you already know how to build a calculus on metric spaces. I'm not going to tell you anything new here, but I'm going to maybe show your intuition a little bit here. Okay, so let's let this be a metric space. Okay, and if U naught is A and epsilon is greater than 0, then we can define a neighborhood. Open neighborhood, open ball, we'll kind of use these terms interchangeably. So we'll define the epsilon neighborhood around U naught to be exactly what you said. I'm just going to look at all points in my metric space that are within a distance epsilon of U naught. Okay, so this is an epsilon neighborhood of U naught. Or we might also call it an open ball of radius epsilon. All right, once we know what a neighborhood is, we can define open and closed sets, we can define limits, we can do a lot. So let's think about open and closed sets first of all. Open and closed sets, they're kind of a fundamental thing that would give us some idea of how this whole space is going to behave. So let's talk about open and closed sets. Okay, we can talk about boundaries. We can talk about all of these things. I don't need to write down the definitions because you already know the definitions. Definitions that we gave at the beginning of semester were just in terms of an open neighborhood. As long as we know what an open neighborhood is, we're in business. So let me not do examples with R or RN because you already know how all this stuff works in RN. Let me try a different collection. So let me come back to all of you. And I'm going to stick this discrete metric on you because that seems more interesting than anything else I could put on you, which might look a little bit too Euclidean. All right, I'm going to write down an open set. That is, I'm going to write down a set of this form, an open neighborhood, and then we're going to ask ourselves some questions about this set. So I need a place to center it. That means I need to pick somebody to pick on. You're sitting in the front row today, so you have volunteered yourself. All right, so I'm going to write down this set. You also have a short name to write, so that will be convenient. All right, I'm going to do a ball of radius 1. The 1 is not particularly small, but let's take it and work with it. So what elements are in this set? Yeah.
Just himself.
It's just himself. So this set is actually a singleton. So you're all alone in this open neighborhood. Okay, we're not used to open neighborhoods being singletons, really, but okay. This is what it is. I mean, we've only got a finite collection of discrete objects, so that's what it is. No big deal. Is this an open set? What is the definition of an open set?
Draw a neighborhood around it and
Draw a neighborhood around what?
any point in the
Any
set.
point in the set. All right, there's only one. I need to check if you're interior to this set. So can I draw a neighborhood around it that stays inside this set? Just any neighborhood. You think no? Well, isn't this a neighborhood? This is itself an open ball. This is how we've defined open neighborhood. So let's choose any thing in the set. Well, there's only one. And we know that we can draw a neighborhood around this. N is itself a neighborhood, an open neighborhood around a reference point. And of course, N stays completely in my set. So this set is open using our usual definitions. It's a singleton. Again, this makes you uncomfortable because your intuition was formed in Rn with the Euclidean metric. I could put a discrete metric on Rn and make weird things happen there too. So it's not even due to the fact that this is a finite set. It has a lot to do with the metric I've chosen here. Okay, so actually this is an open set. You believe me here?
Makes me uncomfortable.
It makes you uncomfortable, that's good. I'm trying to make you a little bit uncomfortable here because we are moving away from Rn now. And your intuition that was formed in Rn is not always going to work when you're talking about spaces of functions or other things that we care about. And they don't want you to take as obvious things that are false, which is very easy to do. All right, what's the boundary of this set? What's that? You think everybody else is the boundary, so you want to have a big boundary. Well, let me ask if you're a boundary point then, since you volunteered yourself here. So, is Gabriel in the boundary? What would it mean for you to be in the boundary?
Taking the metric less than one boundary, measure equal to one.
So what is the definition of a boundary point? I can make a neighborhood. In fact, any neighborhood I make will have something in the set and something out of the set. Well, let's consider a neighborhood around you. Well, one way to do it is just to do this again. I put a neighborhood around you. Let's call this M. Okay, this is an open set around you. Okay, what's in this set? Well, for you to be a boundary point, any neighborhood I draw has to contain a point that is in N and a point that is not in N. So my question, I guess, is, there's only one point in N. Is Luke in this set? He's not. So, Luke is not in this set. So, indeed, this set has no intersection with my set N. But, right? If Gabriel's in the boundary, then any neighborhood about him should contain a point in N and in N complement. But that's how we define a boundary point, right? Any neighbor, how do I can draw around this point? Contain some things inside the set, some things outside the set. That's not true of you, and it's not true of any of the rest of you either, for the same reason. So, everybody who's not Luke is certainly not in the boundary. So we probably don't have a big boundary, yeah. You've seen the problem here too. Luke can't be in his own boundary for the same reason, because I can draw a neighborhood around him but that contains him, but has nothing that's in N complement. Right, so similarly, N is a neighborhood about Luke, but contains no points and complement. So actually, you're not in your own boundary either. So what's the boundary? It's the empty set. There's nothing. And we have other sets with more traditional metrics, I guess, that have no boundary. If I take the set of all real numbers with a traditional Euclidean metric, right, the universal set has no boundary. So there are sets with no boundary. Even on singletons, we're not used to seeing a set that's a singleton having no boundary. Okay, is the set closed? We know it's open. Is it closed? So if it contains all its limit points, I guess, then it's a closed set. Yeah.
Yes.
You think it's closed? How come?
Because you can take any person in the class and draw a neighborhood.
That's right. Exactly. So if I look at n complement is everybody else. And I have to ask myself, is this an open set? And indeed, I take any of you. So any element in n complement, I draw a neighborhood around you, and that neighborhood could consist just of you if I take the neighborhood small enough, and that will stay in n complement. So indeed, for all x in n complement, I can draw this neighborhood of radius 1 around you, which indeed stays in n complement. So every point in n complement is an interior point. And therefore, indeed, n is both open and closed. Yeah?
Can we say that, I also had this question when we were, each of us is an open set, right?
Each of you as a singleton forms an open set, yes.
As a complement.
Yeah.
So the union of us
Would be also an open set, yeah.
is the union and complement plus?
Is the union of the universal set an open set?
No, except you.
The union of all of you except, sure, that would be an open set too.
So can we prove it like this?
Yeah, exactly. So yeah, I mean, actually here, you're getting to it. Everything is an open set. One more, I guess. This isn't so hard to answer, maybe, because we've done most of the work. But I'll just write it down because it does have one little bit about it that's a little bit odd. What is the closure of n? It's just n. Okay, right. So there's nothing tricky about the answer to that question. N bar is the union of n with its boundary, which is n. Okay, which again was this set. It was this open ball of radius 1. Now, when we've worked in Rn, if we take an open ball of radius 1, and then we say what is the closure, we'd usually expect to have a less than or equal to here. That doesn't happen here, and it can't happen here, right? I could make this less than half or less than a third, and it doesn't change what's in this set. But I cannot let this equal 1. That will change the set. So this is the one thing I want to just note. This is not the same as putting a less than or equal to 1 here. Which again, is not what you'd expect if you're working in Rn with a more traditional metric. So I do these examples, not because I can see a lot of practical applications on doing calculus on you guys, but I do it to show you that your intuition may fail you moving forward into other metric spaces. And I don't want you to take some of these things as obvious that really may not be true in the type of function spaces that we're actually interested in. So don't take things as obvious, right? We need to prove them. Even the simple things, we need to check against the definitions and prove them. Of course, once we've proved a theorem, we can use it going forward. But we can't assume things that seem obvious because we don't know what is obvious anymore. Questions? So going forward, we're going to be interested in issues of sequences and convergence. Convergence of stuff is what we care about as applied mathematicians. So that's what we'll do going forward. Let's define sequences. If you know how to define sequences, you know how to define limits. I've given you the one thing that you need to define most of calculus. So we'll start building this up, and then we'll also, along the way, try to see some practical, realistic applications. So I'll leave you there today.